This one, 7. Should we do 7? Is that a good one? Let's do 7. Okay. So, the first thing is I'm giving you the graph and asking you to work backwards to write the equation. So, first of all, in terms of in rectangular coordinates like these graphs, either way, given the graph, write the equation, given the equation, sketch the graph. And then we know that we use this graph to sketch the polar graph, right? Okay, so what is this? This is, what's their center line? Center line's at 2, so we're going to move the whole thing up 2. And then what's the amplitude, or from the center up to the top? Looks like 3, right? 2 to 5 and 2 down to -1. So it's going to be 3 times something. So do we want to model this with cosine or sine? So it looks like sine, because it starts at the midline, but what's the difference? It goes down first, so that means negative sine. And then finally, the period is 4 pi. So it makes it goes through all its output values for a range of 4 pi. And so then, so we're going to have some coefficient here. And when theta, so we want this thing to be 4 pi. When what? When theta, other way around here. When theta hits 4 pi, we want that whole thing to be 2 pi, right? So because we know the period of sine is 2 pi. But we're going to get to that period actually when we hit 4 pi. So when theta is 4 pi, we want the whole thing to be 2 pi. Does that make sense? So we're going to get one full cycle. We know for sine that's 2 pi. But we get that when our value of theta is 4 pi. Therefore, b is going to be what? 1/2. So we're going to have b is 1/2. So that's our equation, -3 sine 1/2 theta plus 2. But then to sketch the polar graph, we're really going to use this, right? And so then we're going to say as theta goes from 0 to pi over 2, or about something close to that. Pretty close. What does r do? So we're thinking r's up here, theta's on here. What does r do as theta goes from 0 to pi over 2? Decreases to 0. So we're going to start at 2. And by the time we get to pi over 2, it's going to be 0. And in between, we have decreasing r, right? R is going to decrease. So what does that look like? We're going to get closer. As we turn counterclockwise, we get closer and closer to the pole. Something like that. So you think about turning counterclockwise and r coming in as you do that, right? R coming in as you do that. And then, from pi over 2 to pi, we go from what to what? 0 to -1. So here we're in this, theta's turning through this quadrant, but what does 0 to -1 mean? Will be negative values will be over in this quadrant. So we're going to go from 0 to -1 when we get to pi. So here's pi -1 right there. And then from pi to 3 pi over 2, -1 back to 0. So again, we're turning in this quadrant here, but they're negative values. So we're going to be up here. We're going to go from -1 back to 0. And then from 3 pi over 2 to 2 pi, from 0 to 2. So 0, r is increasing to 2. Okay. So that takes practice. That's why we've got lots of practice problems. Maybe do some more recitation. All right, are we done? No, because yes, 2 pi is what we expect to be the period, but look, there's a whole different section of the graph here. This is the easy section now. As we go from 2 pi, we can go all the way to 3 pi. What happens to r? From 2 to 5. So here we are at 2 pi, and then 3 pi is over here to the left, and we're going to end up at 5. And r is just going to increase the whole time. It's just increasing, 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 increasing. A nice, smooth arc like that. Something like that. And then back from 5 to 2 as we go the other half of the circle. 3 pi to 4 pi, back to 2. So r, as we go around, r is decreasing, 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 decreasing. So we get this, it goes around like this, and then like this, and then like this. Something like that. Any questions? Did you get something like that? I know these are hard, so you need to practice, get help, sit down with one of us, office hours, to work these out. But it's really about thinking about theta rotating counterclockwise and how r changes as theta turns counterclockwise. And this graph tells you how it does that. Okay. So we were looking at, last time, we looked at 2 sine theta. And we worked that one out. And what did we see for that one? Do you remember doing that one? I'm just going to show you. You can review what we did, but we got when we did that one, we got remember then the first as theta went from 0 to pi, we went out to 2 and back to 0, and then from pi to pi over 2, we went to -2. Let's show our. We went out to -2 and then back to 0. So it, like, when you did a whole period of that graph, 2 sine theta, it actually drew the circle twice. So you really only needed up to pi to get the whole graph. And then from pi to 2 pi, it did it again. Do you remember doing that? And then we said, that looks a whole lot like a circle. So is it a circle? Just because it looks like a circle? So why is it a circle? All right, so if we could change this r equals 2 sine theta into an equation of x and y, maybe we could, that would be more mathematical proof that this is a circle, right? If we had an equation of x and y that we know is the equation of a circle, that circle, then that would be mathematical proof. Just looking at it and say, oh, it looks circular, so therefore it's a circle, that's just, that's not really deduction, that's like induction, right? So that's just kind of guessing. So how can we get equation of x and y out of that? Well, that goes back to what is x and y in polar coordinates? X is? So to get x coordinates from polar coordinates, it's r cosine theta. To get y coordinates, it's r sine theta. So if we could transform r equals 2 sine theta into x and y using these, then we could see maybe if it truly is a circle. So we look at this right-hand side, we say 2 sine theta. Well, that's kind of like y. What's missing? R, right? So let's make it. Let's put an r in there. But if we put an r on the right, we have to. Yeah, so we could multiply both sides by r. We can't just stick an r on one side, but we can multiply both sides by r, and it maintains the equality, right? Can you walk around and make sure that everyone is paying attention? Thank you. So what do we have now on the right? 2y. See that? And then what did we say r squared was? Yeah, by the Pythagorean theorem, r squared is always, if it's the distance from the pole, it always makes a right triangle with x and y, and is the hypotenuse of that right triangle. So r squared is? It looks like we're making some good progress towards an equation of x and y. So let me stop right there. Do you see what we did? So I finagled this so I could use r sine theta was y and r cosine theta was x, and r squared is x squared plus y squared. By multiplying both sides by r, then I have 2y on the right and x squared plus y squared on the left. Does it make sense? So then we think back to our equations of a circle. Equation of a circle is x minus a squared plus y minus b squared equals radius squared. So can we make this thing look like that? Well, that means I've got to move all my x's and y's over. All my x and y terms are on the left. So we got x squared plus y squared minus 2y equals 0, right? So I move the 2y over because all the x's and y's are on the left in the equation of a circle. And then, so we got perfect squares here, right? Perfect squares. So that means I need to complete the square. Remember how to complete the square? So this is just simply x minus 0 squared. That's fine because there's no x term. But this one, I've got to get it to look like y minus something squared. So to complete the square, you do half of the coefficient of the linear coefficient and square it. And that's what you add. So what's half of negative 2? Negative 1, square it. Positive 1. So I'm going to add 1, and that completes the square. Half of the linear coefficient squared. That's what you add, and that completes the square. So half of minus 2 is minus 1. Squared is positive 1. But if I add 1 on the left, I have to add 1 on the right to keep it equal. And now I got x squared plus y minus 1. There's my perfect square. Y minus 1 squared equals 1. Does it match that? Center is 0, 1. Radius, the square root of 1. Because that 1 is actually radius squared. Okay, that right-hand side right now, up there is radius squared. So does that match, right? We thought this was a circle. It is. Is the center 0, 1? Sure looks like it, right? Is the radius 1? The high point was at 2, right? And so that's 1 away from the pole, 1 away from that point, which is at 2. So indeed, this is a circle, center 0, 1, radius 1. And that shows it, proves it mathematically. So polar coordinates, it's based on r, which is like circles around the origin, right? An equal distance from the origin is r. So for instance, what's the graph of r equals 4 in polar coordinates? What are we saying? All points 4 away from the pole. All points 4 away from the pole would be circle, radius 4, centered at the origin. And so we saw r equals 2 sine theta. That makes a circle. So polar coordinates, very compatible with circles, especially centered at the origin, right? A constant value of r is a circle, right? A constant value of r is a circle around the pole. So we have high compatibility with circles. What about lines? Are lines compatible with? Well, it depends. What about theta equals pi over 3? What's that in polar coordinates? It's a line, right? It's a line through the pole, right? Line through the pole. And it's this line right here. See that line right there? And then if we include negative r, we get the whole line, right? For negative r. But what about this line? We could do it. We could do it. Why? Because y is, we could write this in polar coordinates. Y is what? R sine theta. And x is? R cosine theta plus 3. And if I could solve for r as a function of theta. I could move this over. I get r sine theta plus 2r cosine theta equals enough. Okay, and I added what? I added minus 2r, positive 2r cosine theta to both sides. I can factor out an r. And then I get r as a function of theta. So my r as a function of theta means r equals something all with thetas, right? 3 over and if I put that in, so I'll come over here and I'll put in for G here. Three divided by sine theta plus 2 cosine theta. And I'm going to graph G. What line is that? Yeah, it has y-intercept of, so if we now we're superimposing, we're putting the Cartesian coordinates right on top of polar coordinates. Then 0, 3, and 0, x equals 0, y equals 3 would be right there. There's our y-intercept. And then our slope in the xy plane, -2, right? So the rate of change, -2 for every change in x. Y changes -2 times as much as change in x. And that means from left to right, heading down like this. Okay, but what about this equation? So what about y equals -2x plus 3? Simple or complex? Simple. How about 3 over sine theta plus 2 cosine theta? Simple? Weird, right? Weird, complex. Well, that's because these kind of lines aren't really compatible with polar coordinates. So we see that in the equation, and we can do it. We can graph it. But this kind of line is a lot more, so we have a rate of change of y with respect to x, right? So this is much more compatible in rectangular coordinates than it is polar coordinates, and so we see that by the how the function is kind of complex and weird, right? Polar coordinates is much more compatible with circles and sine and cosine graphs, and we've seen the kinds of graphs that we get, these like circular types of things. Cardioids, lemicons, flowers with petals, all these things. Okay, any questions about, so now what are we doing? We're transforming equations or functions in polar coordinates to Cartesian coordinates and vice versa. So it all goes back to using our relationships between r, x, theta, and y. And doing the math. Any questions on that? Oh, yes?
Are you recording?
I think I am. Okay. Yes, please?
When you're doing the center, like 0, 1, is that polar?
No, this is x and y, right? So this equation is x and y, so your center is x minus 0 squared, y minus 1 squared.
That's an x.
So this is all, well, yeah, that's xy because it came from the equation, the xy equation. Yep. Other questions? Okay, so let's do another practice sketch. I've got some more if you need one. You can use the one from last time if you got more axes, but there's a few more new ones. But let's just practice sketching r equals 2 cosine theta plus 2. That's more on the easier side. Hopefully we can do that by now. If not, it's okay. You just got to work at it. But 2 cosine theta plus 2. See if you can do that without technology, no calculators. So we're going to sketch that in the polar plane. Okay, quickly. So you should have gotten this graph. Max is 4, min is 0. Starts at the max, down to the midline, to the min, midline, max. Period is 2 pi. So it hits the min 0 at pi. On its way down, pi over half, and on its way back up, 3 pi over 2. So did you get that first of all? Hopefully. That's the way. We got to have that right. That's how we're going to draw this. And this is easier because it doesn't go negative, right? And the negatives work. It's real tricky. So as we go from 0 to pi over 2, we had from about 4 to about 3 maybe, or around 3 or something. So let's see what this looks like. Where are we here? What? All right, so we're going to go from 4 to about 3 maybe. So here's r decreasing as we increase theta from, I guess, oh no, that's the midline, right? That is the midline. Pi over 2, it's going to hit the midline. Of course. Should have drawn that. Yeah, so it actually hits, I didn't draw it good. Ignore that part right there. Okay. So as you go from 0 to pi over 2, it goes from 4 down to 2. Watch it again. Here we go. As theta increases from 0 to pi over 2, watch r slide down from 4 to 2. Doesn't make sense. And then as theta increases from pi over 2 to pi, r goes from 2 to 0. So watch it's turning from pi over 2 to pi, and r is going to slide down to 0. Boom. And then from pi to 3 pi over 2, it's the third quadrant. Turning through the third quadrant, r is going to increase back to 2. So there's r increasing to 2. And then from 3 pi over 2 to 2 pi, that's the fourth quadrant, 2 to 4. How many got it before I started doing it? Good. Lots of you. Okay. All right, this is called a cardioid. Cardioid, right? Looks like a heart, so it's called a cardioid. So r equals 2 cosine theta plus 2. So let's start talking about some calculus here. dr d theta. So suppose dr d theta equals 3. Let's say dr d theta equals 3. Tell the person next to you what that means. All right, given what? Given a small change in theta? What's true? If dr d theta equals 3, then given a small change in theta, right, how much r changes for that change in theta would be 3 times as much as the change in theta. I hope we've all arrived here. So given a small change in theta, the change in r is 3 times the change in theta. Why? Why does that have to be a small change in theta? Because as soon as you get away from whatever theta you're at, then dr d theta could be different. It could be a different rate of change. All right, so just in a real broad sense, where in this graph might dr d theta be 3? So what does this mean? For a change in theta, r doesn't change. Or sorry, r changes by 3 times as much as theta. So where in this graph might dr d theta be 3? So how about in the first quadrant? Could dr d theta be 3 in the first quadrant? I have a no. Okay, go ahead. Do you hear what she said? In the first quadrant, from 0 to pi over 2, r is decreasing. Therefore, what would dr d theta be? Negative. Right? So all through here, all through that first quadrant, r is decreasing, so dr d theta would be negative. What about in the second quadrant? What's r doing? Still decreasing. So in fact, from 0 to pi, we see it right there. From 0 to pi, r is decreasing. We're getting closer and closer and closer and closer to the pole, so our dr d theta must be negative. What about after pi? What's dr d theta here? What's increasing? R is increasing, so dr d theta is positive, all the way back to 2 pi. So somewhere between pi and 2 pi, maybe dr d theta is 3, because that's where actually r is increasing. So we have a positive rate of change. Does that make sense? What about where would dr d theta be 0? Dr d theta equals 0. What would it mean for a change in theta? It means that when you change theta, what happens to r? R doesn't change. What would that look like in a polar graph? R not changing as you change theta. Where does that happen? You said 2 pi. Agree with that? So 2 pi is over here. So for a change in theta, does r stay constant for a little moment there? Anywhere else? Pi. So as r changes, or as theta changes, does r not change?
Is it undefined out there? Is it differentiable?
Yeah, so actually, that's kind of a weird situation there. Actually, it's right before pi, it's changing very, very, very rapidly. Right? Do you see that? Let's zoom in here. So if we're just, there should only be one. That's just to make it look thicker when I'm zoomed out, okay? That's just one graph. All right, so as theta changes, is r changing slowly or rapidly? Very, very, very rapidly, right? So as you get closer and closer to pi, r is changing very, very rapidly, not 0. And then right after pi, what about, is r changing slowly or rapidly? Very, very, very rapidly. For a change in theta, you're getting a really large change in r because it's heading straight out from the pole. Okay? So actually, at 0, dr d theta is undefined. He was right. Dr d theta is undefined here at pi because on one side it's decreasing super rapidly, on the other side it's increasing super rapidly. So at pi, dr d theta is undefined. What does it mean for dr d theta to be 0? It means that when you change theta a little bit, r stays the same. R staying the same would mean you're kind of staying on one of these circles, right? Staying on one of these circles. So where does that happen? 2 pi, where else? Kind of the same place, 0, right? So the only place where r doesn't change for change in theta is here at 0, and then again at 2 pi. But everywhere else, r is changing, right? Everywhere else, r is changing. We're going through these circles instead of kind of staying tangent to one of those circles. Okay, so that's dr d theta. What about if I'm interested in terms of vertical and horizontal, if I wanted like on the vertical high point, so somewhere up here, somewhere up in here, say between these two angles somewhere, there's a high point. So does dr d theta equal 0 at that kind of that vertical high point? Does dr d theta equal 0? What is dr d theta there? Positive or negative? Negative. See, r is decreased. So for change in theta, so here's constant r, right? Here's constant r. So what is r? Here's constant r through that change in theta. That's constant r. So r is decreasing. We're getting closer to the pole. So if I want to get this kind of this like vertical high point, it's not dr d theta equals 0, but what? Somewhere up here? No. So here's the key. Vertical high point. Vertical high point. What coordinate is vertical? Y, right? So if we want to get the high point vertically, we want to set what? dy d theta equal to 0. We want for it. So now we're kind of like we're crossing. We're meshing them together. We're meshing x, y, Cartesian coordinates and polar coordinates together. We're saying for a change in theta, we want y to have a 0 change. Okay, so what does y equal in r sine theta, right? And what is r on this blue graph? What is r on this blue graph? Values of r are what? 2 cosine theta plus 2. So it's going to be 2 cosine theta plus 2 times sine theta. That's what y equal. That's what the y coordinates equal on this blue graph. So in general, y is equal to whatever our function of theta is. That's what r is, right? Times sine theta. And if I want to find dy d theta, what does that entail then? What do I have to use to find dy d theta? Is it the derivative of f times the derivative of sine? Blank stares. All my life, blank stares. Is it the derivative of f times the derivative of sine? No. What is it? Product rule. Product rule. You have function of theta times another function of theta. Means that if we're going to take the rate of change, derivative, we need the product rule. So dy d theta is going to be derivative of the first times the second plus the first times derivative of the second. So for us in this graph, f prime of theta is going to be derivative of that, which will be negative 2 sine theta. I'm going to use s and c for sine and cosine to save time, okay? So negative 2 sine theta times another sine theta plus 2 cosine theta plus 2 times cosine theta. And then if we want to find the vertical high point or vertical low point, what do? We're going to set this equal to 0. Because at high and low points, as you change theta, y doesn't change. We want y, the change in y to be 0 for a change in theta, right? That's how we get a high or a low point. That's our Calc 1, right? Calc 1 principle. So here we go, ready? Fast. Negative 2 sine squared theta plus 2 cosine squared theta plus 2 cosine theta. equals 0. So it's going to be very helpful if we can get everything in terms of either sine or cosine. Since I have a cosine squared and a cosine to the first, I'm going to change the sine squared into cosines. So we can use the Pythagorean identity. Sine squared equals 1 minus cosine squared. So when I add everything together, I'm going to get 4 cosine squared plus 2 cosine minus 2. Did I do the math right? I can divide everything. I'm equal to 0, so I can divide everything by 2. So I got 2 cosine squared plus 1 cosine minus 1. And then what do I have? I have a quadratic. I have a quadratic in cosine, so hopefully I can factor that. Like it's 2x squared plus x minus 1. So hopefully this will factor out. I think it does. 2 cosine theta, so we got to multiply to -1 and add to +1. So I think we go +1 here and -1 here. So either this could be 0 or this could be 0, right? So in this case, if 2 cosine theta minus 1 equals 0, what do we get? Cosine theta equals +1/2. Unit circle, where does that happen? Pi/3 or -pi/3 or 5pi/3. Where does cosine theta equal -1? Pi. So do these answers make sense? Does one of these angles, pi/3, 5pi/3, or pi, look like it could be in this range here? Yeah, pi/3 right there. Our high point. How could we find the r value at pi/3? Just plug it into the function, right? So plug pi/3 in. We'll get that r value. How could we get the y value? Plug it into here, right? So this gives you y for theta. So plug pi/3 into that. It'll give you how high it gets in terms of y. Okay? 5pi/3 is the low point. There's 5pi/3. That's the very lowest it gets vertically. What about theta equals pi? Well, that's what we were talking about before. So that's where it flattens out. It will flatten out right at pi there. When I zoomed in, you saw that y doesn't change for a change in theta. R is changing very, very rapidly, but y doesn't change. It flattens out vertically. Any questions?